Imagine typing a support search for my package never arrived into a database that only stores the words shipment lost in transit. A plain keyword search finds nothing, not one word matches. Yet a human reading both lines knows they mean almost the same thing. That gap is exactly the problem vectors solve, and it sits at the mathematical core of modern artificial intelligence, especially the technique known as retrieval augmented generation. Vectors give artificial intelligence a way to run fuzzy, meaning-based lookups instead of rigid keyword matching. When someone asks a complex question, vectors let a system judge abstract meaning and pull the exact piece of context it needs out of a massive database. To understand how this works, we have to look at how large language models are built, because the field splits into two completely different architectural families. The most common family, the one powering tools like GPT, Claude, Gemini, DeepSeek, and Grok, is the autoregressive language model. It is trained to do one job: take a sequence of text and predict the single most likely token that comes next. It is called regressive because it keeps looking back over everything it has already produced to decide what comes next, one token at a time. Here is the loop in action. Feed in the words "the cat sat on the," and the model predicts the next token, mat. That token gets appended to the input, so the model now sees the cat sat on the mat, and it predicts the next token after that, maybe a period, maybe the word, and that new token gets appended too, and the cycle repeats. Run this loop a few hundred times, each token feeding back into the next prediction, and that is how an entire paragraph's built, one token at a time, shaped by patterns learned from enormous amounts of training text. There is an entirely different family of language models, known as encoder models, or embedding models. Unlike their autoregressive cousins, encoders do not generate text piece by piece. An encoder takes a complete sentence all at once and produces a single output meant to capture the meaning of that entire sentence mathematically. This is powerful for classification tasks. Feed an encoder a customer review like, "This flight was delayed 6 hours and nobody apologized," and it can output a single tag, negative. But the most important job these models do today is turning raw text into a structured list of numbers called a vector embedding. Here is that idea made concrete. Picture the sentence, "The puppy happily chases the ball," going into an encoder model. The model does not reply with words, it replies with numbers. Say, for simplicity, outputs 10 numbers: 0.5, negative 0.82, 0.44, 0.91, negative 0.37, 0.06, negative 0.59, 0.28, negative 0.14, and 0.73. That full set of 10 numbers is the complete vector. In mathematics, a list of numbers like that is a coordinate in space. 3 numbers would be an x, y, and z coordinate in our ordinary 3-dimensional world. 10 numbers place that sentence at a coordinate in a 10-dimensional space nobody can actually picture, but the math works the same way. Production systems push this much further. OpenAI's text embedding 3 large model maps text into 3072 dimensions, and the open source all-minimum L6v2 model uses 384. Every one of those dimensions is one more number pinning the sentence's meaning down more precisely in mathematical space. This is where newcomers usually get confused. What is the difference between a token and a vector? Both involve numbers, so they look alike, but they play opposite roles in the pipeline. Tokens are the raw input that goes into a model. Vectors are the deeply analyzed output that comes out the other side. Here is why any of this is necessary in the first place. A machine learning model, underneath everything, is a vast engine built from addition and multiplication. It cannot read the word apple or the word run. It only understands numbers. So text has to be converted into numbers before it ever reaches the model, and that conversion is called tokenization. A tokenizer is a simple, deterministic piece of code that maps chunks of text to fixed numerical identifiers from a set vocabulary. Given our sentence, "The puppy happily chases the ball," a tokenizer strips away all meaning and chops the text into pieces. The word that becomes identifier 463, puppy becomes identifier 8432, and happily becomes identifier 1209. Rarer or made-up words get split even further. A word like unhappiness might come apart into 3 separate pieces, unhappy and ness, each with its own identifier, because the vocabulary would rather combine small known pieces than store every possible word. None of this takes any intelligence. Tokenization is a rigid, mechanical step that turns raw strings into basic numerical input, nothing more. Vectors are the sophisticated output generated after those plain token identifiers pass through a large language model. Once that list of simple identifiers moves through the model's neural layers, the model works out the syntax, the relationships between words, and the underlying intent of the whole sequence. The resulting vector embedding is not just an identifier map, it is a dense list of decimal numbers capturing the full meaning of the text. Here is the payoff, pass in a completely different sentence. A young dog joyfully pursues a toy. Its token identifiers look nothing like the identifiers for the puppy happily chase the ball. Not one number matches, but run both sentences through an embedding model, and their output vectors land almost on top of each other in vector space. Measured with cosine similarity, the standard way to score how closely two vectors point in the same direction, those sentences might score above 98% similar, because the model has grasped that the underlying idea is nearly identical, even though the words are completely different. For anyone who wants the fuller picture, the internal reality is a little more layered than the simple idea of tokens, vectors out. Inside a large language model, data exists as vectors constantly shifting from one hidden layer to the next through the whole transformer network. Even at the very first step of an autoregressive model, incoming tokens get mapped to an initial embedding vector before any real processing happens. That first step is literally called the embedding layer. But for everyday understanding, this rule holds up. Tokens are the raw, uncontextualized input to a system, and vector embeddings are the rich, high-dimensional output that unlocks things like retrieval-augmented generation and contextual search.